Okay, this time we're going to be looking at a diode. Now, the diode is a device that basically allows electricity to go one way. Unlike the resistors and capacitors, it is an active component. In other words, it can actively switch electricity and requires power to operate, as opposed to just slowing things down or storing it. And I have this particular diode hooked up in this circuit with an LED. And when I turn the power on, this is what's called forward biased. So if we look at conventional positive current, it comes this way through like this, and this will allow it to pass through, and then the LED comes on. Now what we can do with this diode, I'll take the power off for a second, and we'll flip this around so that it's reverse biased. In other words, the positive and negative ends are reversed. And if I put power on it, the light doesn't come on. And that's because the diode is now blocking the electricity coming in from the power supply. So diodes are useful for changing the preventing electricity from going the wrong way. We can use them for a bunch of other things as well. So what's happening inside the diode that's making this happen? Well, inside the diode we have two chunks of materials that are put together in contact. One's called P-type material, the other's called N-type material. Now, usually nowadays they make these guys out of silicon, and the P-type material has some impurities put into it. It's doped, and the impurities cause there to be extra holes where electrons can go. Whereas in the N-type material, it has impurities or doping that cause extra electrons to be present. And this little area in between is called the depletion region. And the electrons on this side went across the depletion region to get over into the holes over there. So in conventional current, in other words, we put the positive on this side. So if we forward bias, we have our positive over here and our negative over here. The electrons want to move this way to the positive, and they can, because when they come into the diode here, there's space for the electrons to move over this way and then come on out on this side. However, from reverse biased, the negatives over here and the positives over here, the electrons are coming in this way, and they're trying to get across this P, and they can fill this up. But then they get here, and there's all these electrons in the way. So they can't get through. That stops the electrons from traveling through. Of course, if I put enough voltage across reversed, they'll just push on through. Now it's the breakdown voltage, but generally we don't want to put the breakdown voltage on a diode because that usually damages it. Okay, so when we have to hook our diodes up correctly, or else they're not going to work. And so we want them forward biased. So that would mean, so if this the diode symbol here, so this would be the plus side of it, and this would be the minus side of it. This is also a diode symbol. They're just differences. They're just filled in. And so how do we tell which of these is which on a real diode? So here I have a picture of a diode, and if you notice, there's a very hard, kind of faint silver band right there. Okay, so right there is a silver band. That silver band is analogous to this little chunk of this here. So this is the positive side of the diode, and this is the minus side of the diode. So if you hook that in that direction, so you have the positive side of the circuit over here, the negative side of the circuit over here, it's forward biased. If you put the positive here and the negative here, it's reverse biased. And it won't allow electricity to pass through. Okay, so I have this array of multimeters to show what's happening in this diode circuit. So basically we just have power coming in, going through a diode, which then goes through a resistor to act as a load. And so if I turn the power on, you start at about 1.7 millivolts. This multimeter is giving us the voltage across the whole circuit. This multimeter is giving us the voltage across the diode. And then this multimeter is giving the voltage across the resistor. Now at 1.6 millivolts, so basically we're off, there's no voltage coming through that diode, which is kind of interesting. So let's turn this up a little bit. So we're up to about 1.6 millivolts. Still no voltage going through our diode. Turn that up a little more here. Okay, we're now at 0.3 millivolts, and finally we're getting a little bit of voltage. If we go back down to say 14, 15 millivolts, nothing there. 20 millivolts, still not a lot there. And then when we break 2.5 millivolts, we start getting a little flat. We get 5 millivolts across our resistor, and then if we start bringing our voltage up, we're now at about 0.8 millivolts coming out of the power supply. So at 0.8 of a volt, and here we have 400 millivolt drop and 300 there. So if we bring this up to, let's bring this up to a full volt, a little bit more. We're now losing about, there's a voltage drop of about 0.4 volts across our diode, and we're now at 0.8 there. So which is obviously that minus that gives us that. Let's put this up to 2 volts and see what we get. Okay, we're now at 2 volts. So we've got a 0.478 voltage drop across our diode, and then the difference shows up there. And we turn that discontinues on. So what this shows is that there's a minimum amount of voltage needed for the diode to turn on. Okay, if we're below that minimum amount, our diode won't turn on. So once we get above that minimum amount, our diode turns on. And then as the voltage increases, the diode then settles down to a amount of voltage that it drops. It steals some of our volts. So we're up to 8 volts, 7, 8 volts. We're losing about half a volt across our diode now. So that's something to remember about diodes. They need a minimum amount of voltage to work, and there will be a voltage drop across them. So they will basically steal some of the voltage. So something to keep in mind when using diodes. Okay, so we're going to look at one of the functions of diodes, and that's to rectify. And when a diode is rectifying, what it's doing is basically it's taking AC electricity and turning it to DC electricity. So what I've got here is, this is just coming off my function generator, but I have an AC 60 Hertz signal coming in. That's ground right there where that yellow line is. That's the second channel. And as we can see, it's going both ways. It's not DC. It's going positive and negative, positive and negative, positive and negative. Now, I've got a diode here, and I've got my other oscilloscope probe, and if I connect that up, like so, you can see now that our second channel is DC. It goes up, comes down, but when it gets to 0 volts, it stops, and then there's nothing, and then it goes up. So this is a DC signal now. I mean, it's a varying DC signal, but it's DC. The current is only going in one direction. I can move one of these a little bit so we can see that a little better. So we can see our second channel only going up and not going down below ground. So that's one of the things that we can use diodes for, is to take AC electricity and turn it into DC electricity. A very common type of diode, and one we encounter in everyday life quite frequently, is the light emitting diode, or LED. So I've got one right here. That must be a green one. It works just like a regular diode. This one's currently forward biased, and so as it's forward biased, electricity goes through it, it emits light. If I take this one and flip it around so it's reverse biased, it doesn't turn on because it's a diode and it won't let electricity go through backwards. Turn it back around again, and forward bias, we turn on again. Now if you notice, we also have a little resistor here. LEDs can only handle so much current, and it's usually not a lot, so generally you have to put a little resistor in the circuit to limit the current. It's called a current limiting resistor, and this is a 470 ohm one. That's usually a good value for most LEDs. and it keeps your LED from getting damaged. If you don't put the current limiting resistor in, the LED will burn out, usually, sometimes quite spectacularly by making a big pop sound. So always remember to put that current limiting resistor in. Now we also have some other interesting, another LED here, because they come in different shapes and sizes and colors. And this one is interesting because there's actually two little LEDs inside this guy. So if I plug them in one way here, we get a green light, and that means that the green LED that's inside here is forward biased. The other LED that's in here is reverse biased and it's not turning on. So if I turn this the other way, I get a red LED, red color, because the red LED in there is turned on and is forward biased, and the green one's turned off and is reverse biased. So that's LEDs. So things are just diodes like other diodes, except they give off light, and they're used all over the place these days. And I have one right here. And photodiodes are kind of cool. They react to light, obviously. If we forward bias a photodiode, and I'll just connect it directly to the voltmeter here, it actually makes a current. It's basically a small solar cell. If I block the light off, you can see the voltage goes down, and then I bring it back, comes back up. But we're looking at, only about 300 millivolts here. There's not a lot of voltage on one of these things, so there has to be a little bit of amplification. And it's actually quite common to hook these up in reverse bias. So I'm going to do that here, this little circuit here. And what I've got is I've got the photodiode hooked up to a transistor. The transistor here is amplifying the rather small current from the photodiode, and the photodiode is hooked in backwards, so it's in reverse bias, and that'll allow just enough current when the light's on it to turn on this transistor, which should turn on this little LED here. So if I turn the power on, the LED turns on, and if I bring the light a little closer, it gets a little brighter. If I take the light away, it gets a little dimmer. If I take the light away from it, it goes off. So that's how the photodiode works. Now this is, like I said, is in reverse bias, and but because it's such a small amount of current, we have to use that transistor to actually turn the LED on. Okay, so what we have here is a Zener diode hooked up to help regulate the voltage. So that's because Zener diodes have very precise breakdown voltages, and we can use that to keep the voltage where we want it. So what I've got is I've got this hooked up to my power supply, and right now it's sitting at 0 volts, and this is hooked up through the Zener diode there. So as I turn the voltage up on my power supply, you'll see that voltage goes up here as well. So at 1 volt, we're at 0.9 volts here. There's a current limiting resistor in there, and that's why that's a little bit different. But as I go up, now to 1.5 volts, 2 volts, 2.8 volts, 4 volts. We're now at 5 volts, and this is kind of peaking out around 2.2 volts or so. Now it's 7 volts. And so it's keeping our voltage down around 2.5 volts. And that's one of the things that Zener diodes get used. Now, it's not very useful in a circuit like this simple if there's a lot of current, because the Zener diode can't really handle that. But they're used to provide voltage references in power supply circuits. And if we go back down, they'll start matching up again pretty close, and then back down to off. So that's our Zener diode, showing us that we have it in reverse biased, and how we use its breakdown voltage to control the amount of voltage coming out to the circuit here.